Example 9.1, consider two straight parallel wires labeled A and B perpendicular to the YX plane. Each wire carries current I, but in opposite directions. A, use the right-hand rule to determine the net direction of the fields at point 1, 2, and 3. B, now mathematically determine the magnetic fields at points 1, 2, and 3. And C, determine the magnetic field as X gets much bigger than D along the positive X-axis. So the question that we have to answer is, what is the physics of the field? I think what we should do here is that we should start by sketching the magnetic field first. So when I'm looking at this thing, I would not expect perfectly symmetric field lines because we have superposition of two magnetic fields. So I'm going to say that here's my first, and this is going to be my wire A. Then this guy is going to be my second wire, which is my wire B, and I'm going to draw them different colors. So if I'm really close, I would expect that that field should dominate and I should have a fairly symmetric magnetic field. But now what happens is that I start to see a skewing of the field. So I would expect that I'm going to get something like this, where it's not fully symmetric. And if I start to do the same thing over here, I'm going to get something like this. You're seeing the skewing of the field. And then if I get further out, I'm expecting that the field to look something like these guys right here. So you're seeing the bunching of the field lines in between. And since the density is higher, that's telling us that we should have a stronger magnetic field there. So if I'm looking at my red, I'm squeezing right into here. In my green, I'm squeezing right into there. And you can see that the highest density of the field is in between. So now if I just started putting in my directions of the field, it's got to look like this. And there's my magnetic field. So the red is A, the green is B. So I can call this the magnetic field due to wire A, the magnetic field due to wire B. So now if I'm looking at points, I'm going to say, this is going to be the first point I'm going to look at. This is point 1. And you could see I expect, because the field lines are spread out, I expect a weaker field. And then we're going to calculate where the field is strongest at point 2. And then over here, we're going to call this point 3. So point 3 is closer to B than 1 is closer to A. So our axis here is that this will be our x-axis, and this will be our y-axis. So let's write down a couple of things of what I just said here. First thing here is that the individual fields have symmetric circular patterns. But the combination of two wires due to superposition are not symmetric. Since we expect that the net field to be a combination of these two magnetic fields. So there's going to be partial, cancellation because of one of the fields being opposite. To calculate the magnetic field at points 1 and 2, we're going to have to use superposition to do that at points 1, 2, and 3. So now, using the right-hand rule and knowing that the field of an infinite wire is proportional to 1 over x, we can rank the magnitude of the fields by looking at the field pattern. We could see that the highest density has to be at point 2. So we know that has to be the largest. And when you look at the density of field lines, 3 has a higher density of field lines than 1. So it should be the magnetic field of 3, and then the magnetic field of 1 being the smallest. So now let's look at this in detail. Here is a more detailed picture using superposition. So when I'm looking at the magnetic field, here's what we see from our picture. For starters here, we have this guy right here. This is wire A. And then we have our second wire, B. So if I'm looking at point, so I know right here, this is point 2. And then point 3, so if we're looking at distances here, so I'm going to say that this is point 3. And then over here, so we're going to have to be farther. This is going to be point 1 right here. So let's start with point 1. So if I look at point 1, there are 2 magnetic fields. So if I look at the magnetic field of A at point 1, we could see that this magnetic field should be smaller. And that's going to be the magnetic field of A due to 1. Now, if I look at the magnetic field of B, that's going to be going upwards. So what I'm seeing here is that this is going to be the magnetic field of B at point 1, you could see how we have partial cancellation. So I expect the field here to be very small, and that's what I'm going to call the magnetic field of 1. Now, if I'm looking at the magnetic field of 2, as we saw up here, the fields are in both directions adding together. So superposition then says something like this. I'm going to get a field that's going to be, let's say, this big. Nope, I'm going to make that bigger. So this is going to be the magnetic field of A at 2. This will be the magnetic field of B at 2. So then the net field should be twice this. So it should be like this. And that's the magnetic field of 2. Now note that 3 is closer to the center than 1, so they should have larger magnetic fields. So in this situation, we'll say that here, the green field is pointing down. So let's say that this guy is going to be, let's say, this big. So that's going to be the magnetic field of B at 0.3. This field, because it's much farther, is going to be smaller. And that's going to be the field of A at 3. So when I look at this field, I'm going to say that it's going to be, let's say that I'm going to try to scale this, which is not realistic, but that's going to be the field at 3. So when I look at the rankings again, right, if we look at the rankings, we can clearly see that the blue fields tell us that the rankings make sense here. So again, this is our x-axis. This is, I'm going to call that positive y, and I'm going to call that positive x. So now all we have to do is calculate these fields. Let's go do that. So B here tells us to calculate the fields B1, B2, and B3. So let's look at point 1. So the point 1 field. So if I look at distances here, it's looking something like this. So we can see here from point 1, from what we've already seen up here, the fields are in opposite directions. So superposition dictates that we have to do that. So the fields are in opposite directions. To each other. And when I start to sketch out their picture, we need to start talking about distances here. So these are not scaled. So I'm going to say that this is the field of A. This is going to be the field of B. And then I know here that they tell us about the distances. So I know that this is the y-axis right here. And I know that from our picture here, they tell us that this distance right here is D. That distance is D. And then point 1 is 2 times D. So this guy right here is actually point 1 right here. And so if I look at this distance right here is 2D. And that's how far. So now I know what the distances are. So when I start to look at the superposition of this, we've already saw here that the magnetic field of due to wire A is larger than the magnetic field due to wire B. And so we're going to have some net field that then is going to look something like this. So now I just have to calculate these fields. So what do we know about these fields? So where I know that the magnetic field of A has to be in the negative y direction. So I have to include that negative sign. So if I look at this thing, I'm seeing something like this. I'm seeing that we know that the magnetic field of an infinite wire looks like this. And we know that this has to be in the negative y direction. So I can see that the distance from A is 2d. So when I write this out, it has to be 2 pi 2d into mu naught I. Again, I get this direction right here. And so finally, I get a value of 4 pi d divided into mu naught I, and that's going to be the direction of the magnetic field and its strength. Now I'm just going to repeat the same thing with B. So if I look at B, note that we have the exact same equation. So I'm just going to use the equation from above. So this should then be 2 pi times 4d, because it's 4d away. So in this case, we still have this here, but the difference here is that this is in the positive direction. And so if we write this out, this will then be 8 pi d of mu naught I in the positive y direction. Applying superposition. So superposition tells us that the field B1 is then going to look something like this. So I'm going to have B1 is then going to be the combination of minus B1 due to A. And I'm going to now say that this is in the y direction. And then this guy is going to be the magnitude of B1, but this guy is positive in the y direction. So then if I add these together, here's what I get. I get 4 pi d mu naught I minus 8 pi d, where I factored out a minus sign. And this is again in the y direction. So the field is now minus 8 pi d mu naught I in the y direction, and this is the magnetic field of 1. So let's go to field 2. So this is the point 2 field. As before, we see here from the overall field, right? We can see here is that these field lines are pointing in the same direction. In fact, I don't know why I just didn't do that. I can just copy this and bring this with me. If I copy this, we can then see here is that the fields point in the same direction. Let's see if we can just paste this guy in here. So if I look at this field, what we're seeing here is that we know what these distances are. From here to here, this distance is little d, and that distance is little d. And again, this is our positive x, this is our positive y. So we just got to add these. So if I add these, we can see here that where the magnetic field of A2 is again going to be equal to 2 pi x mu naught I. And in this situation, we could see here is that this is in the positive y direction. But at d here, we could then write that this is 2 pi d of mu naught I. And again, in the positive y direction. I could do the exact same thing with b. So here, it's going to be the exact same magnitude. So this will be 2 pi d u naught I, and this will be in the positive y direction. So then, superposition gives that B2, which will be a combination of A contribution plus B contribution, that when we add these together, we then get that we're adding 2 pi d mu naught I plus 2 pi d mu naught I in the y direction. So then the field is then going to be pi d mu naught I in the positive direction, and this will then be the magnetic field at 2. Now, if I repeat this process for 3 up here, I could just copy and modify this. So let's look at this thing and see if we can do that. So now we're at point 3. These fields point in the opposite direction. So if I have my magnetic field here of A, and I have my magnetic field of B here, then what we have here is that we have that point 3 is right here. This is going to be point 3. So, but what about the distances? This distance, okay, this is the origin right here. So we know that this distance from here to here is 2d, and then the distance from here to here, that distance is then going to be 3d. So when I look at this field, we could see that the green field should be larger, whereas the red field is going to be smaller. So that the net field roughly should be about this size right here. And it should be in the negative direction. So now we could just write these guys out. Where if I look at the field of A, we can immediately write this to look something like this. So we know it has to be 2 pi 3d mu naught I, but in this case, this is in the positive y direction. But if I look at the field at B3, this will then be 2 pi d, which will be mu naught I, but this is in the negative y direction. Following superposition again, so this gives us then that B3 is then going to be the combination of these guys. So in this case, I'm going to get a positive BA3 minus BB3, and this will all be in the y direction. So if I plug in my values here, I'm then going to see that this will be 6 pi d mu naught I minus 2 pi d mu naught I, all in the y direction. And then I'm finally going to get minus 3 pi d mu naught I in the y direction. And this will then be the magnetic field at 3. So if I look at the rankings of these guys, what do I see? The magnetic field at B1, that has a magnitude of 8 pi d mu naught I. The magnetic field at 2 reads pi d mu naught I. And the magnetic field at 3, that read 3 pi d times mu naught I. And we could immediately see here that the initial rankings agree with the mathematical ones. We can clearly see that B2, which is equal to pi d mu naught I, is definitely bigger than B3, which is 3 pi d. And then B3 is definitely bigger than 1, which is 8 pi d times mu naught I. So it agrees with what we expected. Now let's go to part C. This last part of this question is somewhat similar to the electric dipole example from chapter 2. So we want to compare the two situations. So let's compare the two situations of an electric dipole versus magnetic maybe I shouldn't say magnetic, maybe two wires with opposite currents. So if I look at a dipole, I'm going to be looking at something like this. So we had a dipole. We had a positive and we had a negative charge. So if I'm looking at this, we're saying that these guys are separated by a tiny separation, which we'll call D. And then we're going to pick a point P where P is far away. So if I look at the dipole at this point here, we're going to have an electric field for a dipole right here that points in that direction. Actually, that's incorrect. That dipole field is pointed in the opposite direction. But it's the same analysis that we did before. I should have just reversed the positive and the negative. And then we would have had what I looked at. So when I look at this situation here, we saw that if we took the limit as x is much, much bigger than d of the electric dipole, and I look at its magnitude, we ended up with a relationship that looked like it's 2 pi epsilon naught x cubed over qd. So now I want to do the same type of thing here, but with my magnetic fields. So here we have our wire A, we have our wire B, and again, from the center, we have the same separation. So this guy is little d, this guy is little d, and then we're going to pick a point P here. And what we're looking at is that we're actually looking, even though I didn't mention it, this is the distance x here. And we already calculated this thing, and we know that the field is going to be pointing down here. So we know that the net field is pointing down. So the question that we're asking is this. In the limit as x gets much, much bigger than d, what does that magnetic field tell us about two infinite wires? What is that equal to? What is that? Well, we got to calculate that, so let's calculate it. To calculate the net magnetic field, we have to shift our displacement vectors. In other words, if I have a magnetic field like this, oh, excuse me, wires, and if I set my origin right here to be x equal to 0, then I could come in here and just say, okay, so if this is my distance here, I know that this distance here is d. I know that this distance here is d. But if I pick my point here to be point P here, then the distance between here and here is going to be my distance x. So we know that the net magnetic field at this point has to be pointing in this direction right here. So if I shift my displacements, we can see here is that RA should then be what? From the origin, we can see here is that this guy has to be x plus d. And if I look at RB, that has to have a shift where I have to change that by minus d. So then the net field at point P is then going to be this. So I'm going to have my magnetic field, of course, and we're talking about two wires of opposite current. And then I'm going to have my magnetic field due to A, my magnetic field due to B. And if I add these together, I'm then going to have 2 pi x plus d. And that's going to give me minus mu naught I. And then I'm going to get 2 pi x minus d mu naught I. And of course, this will be all in the y direction. So focusing just on the magnitude, because we know the direction, focusing only on the strength slash magnitude of the net field, we can rewrite that. If I look at this thing here, I could then rewrite this field, and it's going to read that this will then be pi of d squared minus x squared. And this will then be minus mu naught ID in the y direction. So now, if I look at the limit as x is much, much bigger than d of these two wires, of opposite current, I'm then looking at the limit. So if I pull out all of the constants, I'm going to get mu naught ID divided by pi. Then this will be the limit as x is much, much bigger than d here of d squared minus x squared over 1. So then I can approximate that field by pi x squared mu naught ID, and this will then be the field of two wires with opposite currents. So now I want to interpret this. So the first thing is that if we compare, so let's compare two fields for the dipole. Let me say for the point charge versus the dipole, and a single wire versus two wires with opposite currents. So if I look at the electric situation, I see that I have, so if I look at the electric field of a point charge, this field is proportional to 1 over x squared. And if I compare this to the dipole, this is proportional to 1 over x cubed. So we can clearly see that right here, this is a stronger field. This is a weaker field. So, so the question is that why weaker? It's because of superposition. What did superposition do? Well, it reduces the field at that point. Now, if I look at magnetic fields, what do we find? We find here is that the magnetic field of a single wire was proportional to 1 over x versus the magnetic field of two wires. Of course, these wires have opposite currents. And you could see here that this is also proportional to 1 over x squared. Again, when you're looking at this is stronger. And why is this stronger compared to the two wires? Because of superposition again. And this will be weaker. And if we ask the same question, why? It's because we have a superposition reduction. That's why. So they play a very, very similar role here. So the last thing I want to look at is that I want to plot these. So now I want to plot the field of a single versus two wires. And so when I look at this thing, the behavior, in my opinion, is pretty surprising. So if I look at a single wire, so this is the magnetic field as a function of X. So if I look at the field of a single wire, I didn't write it all in detail. It looks something like this. Okay, so this is going to be the field of a single wire. So it turns out that if you look at this mathematically, they match as they approach infinity, as they approach zero, and then they also match as you go towards infinity here. So then this is the magnetic field of two wires with opposite currents. So they match very well when you get the asymptote as you approach zero and as you approach x equal to infinity.